Come in, find your comfortable place, settle down, let the noise of the day just fade away. The world outside is finally quieting down, and this is a space for your mind to do the same. We are here together to turn our thoughts outward, away from the small worries and lists and up toward the vast, silent wonder of the cosmos. My aim here is simple. I want to help you find a little stillness, to help you relax, to contemplate, and maybe to drift off into a peaceful sleep. We'll explore the great wonders of science, the story of the universe, not as a lesson, but as a quiet meditation, just a chance to wonder. Before we begin, a small gentle request. If you find comfort here, if this space helps you, perhaps you could leave a like or subscribe. It costs you nothing, but it helps this channel and my journey of sharing these stories more than you can imagine. Thank you, truly. Now, let's take a slow breath. Let everything go, and let's begin. Tell us a little about the most magnificent curiosities of the universe. Well, I've been thinking a lot actually about the beginning of it all. The very beginning, the moment before moments existed. You see the Big Bang, it's not just a bang, that name, it's a bit misleading. It makes you picture a firework, a flash of light exploding outwards into a dark empty room. But it wasn't that. It wasn't an explosion in space. It was the birth of space itself and time too. There wasn't anything before it. No space to expand into. No time ticking away. No empty dark room waiting for a light. Just nothing. Or perhaps something we simply don't have the words to describe. It's a strange thing to grasp, isn't it? Our minds are built for a world of cause and effect, of befores and afters. But here, the word before it loses its meaning. It's like asking what is north of the North Pole. And then, suddenly, there is this moment. This singular point. A state of energy so concentrated, so hot, so dense, that all our physics, all our equations, they just stop, they break down, they can't see past that veil. And it expands. It doesn't explode outward, it unfolds. The space itself begins to stretch, and as it stretches, it creates distance, it creates here and there, and it creates time, the flow of moments, the clock begins to tick. This expansion in its very first fraction of a second was incredibly fast. We call it inflation. It's a staggering idea. In a sliver of time so small it's hard to even write down, the universe swelled exponentially, from something smaller than a single atom to something unimaginably vast. And as it stretched, it became smooth, almost perfectly uniform, and it cooled. Almost, but not quite. This is the crucial part. It wasn't perfectly smooth. In that first fiery moment, there were tiny fluctuations, ripples, just the natural unavoidable jitters of quantum uncertainty. And as space itself stretched during that incredible inflation, those microscopic ripples were stretched with it. They were magnified, frozen into the very fabric of the cosmos. Those little imperfections, those tiny patches that were just a fraction denser, they become everything. They are the seeds from which gravity would later grow every galaxy, every star cluster, every star, every planet, and eventually us. But I always stop and ask, why? Why did it happen at all? Why did that singularity, that point of infinite potential, even exist? Was it inevitable? Was it just an accident? This is where the ideas get even more wonderful, more strange. There's a serious and beautiful idea that the universe might just be a free lunch. You see, the total energy of the universe, all of it, might add up to exactly zero. How can that be? Well, you have all the positive energy, the energy of matter, the stuff we're made of, the energy of light, of radiation. But then you have gravity. And gravity in this equation is negative energy. It's the force that pulls things together, a kind of cosmic debt. And it just might be that for every spark of positive energy, there is an equal and opposite measure of negative gravitational energy, a perfect balance. And if the total energy is zero, then maybe, just maybe, you don't need anything to create it. It can just appear from nothing. Some physicists call this quantum tunneling. The idea that a whole universe, our universe, could simply fluctuate into existence from a state of nothing without violating any laws of physics, because in the end, it costs nothing to make. What a thought that all this majesty, all this structure, all this life might just be nothing rearranging itself. And that brings us to nothing. What is it we call it? The vacuum. empty space. But the more we look at it, the more we understand, the more we realize it is not empty. Not at all. The quantum vacuum is the most restless, the most vital, the most creative place in the cosmos. It is not a void. It is a seething, fluctuating field, a sea of energy. At every single point in space, and even in the darkest, coldest, most empty region, things are happening. Particles and antiparticles flickering into existence and annihilating each other in a flash, too fast to be seen, too fast to be caught. We call them virtual particles. They are the foam on this deep, invisible ocean of energy. And we know this isn't just a theory. This energy, this pressure from nothing is real. We've measured it. There's something called the Casimir effect. If you take two perfectly smooth metal plates and place them incredibly close together in a perfect vacuum, they will be pushed together, not by gravity, not by any force we know. They are pushed together by the vacuum itself, because the ocean of energy outside the plates is greater than the energy between them. The vacuum also exerts a pressure. And this brings us right back to the beginning. Those tiny ripples, those fluctuations that were stretched by inflation to become the seeds of galaxies, they were the fluctuations in the quantum vacuum. It was the vacuum writing the first draft of the cosmic story. And it leads to the most profound thought of all. If the vacuum is this restless field of potential, this thing that can spawn particles and exert a real force, then maybe the universe itself, our entire cosmos, was just one enormous fluctuation, a spontaneous event, a bubble of space-time born from that energetic restless nothing. So this idea of the vacuum as a void is just not accurate. It's more like a field of potential, a restless ocean of possibilities. And it may be the very source from which our reality first emerged. Not a void, but a kind of womb, a cradle, a starting point, filled with everything, and yet nothing at all. You know, it's hard to say how many there are. I mean, how many universes. We grow up with this word, the universe, singular, as if it's the only one, the container for everything. And for most of history, that's what it was. Everything we could see and everything we couldn't. It was all just this. But the idea that this is the only one, the only reality, that's starting to seem, well, not wrong exactly, but incomplete. The more we look, the more we calculate, the more we push our theories to their limits, the more it looks like there might be other universes, parallel realities, the multiverse. And it's not science fiction anymore. Not really. It's one of those things where the equations, the mathematics that we trust, the ones that describe our world so perfectly, they start leading you somewhere strange, somewhere you didn't expect to go. Take inflation, for instance, that moment we just talked about. That incredible, impossible stretching of space in the first fraction of a second. It explains so much about our own universe. Why it's so big, so uniform. The theory works beautifully. But the physics of inflation, it has a strange consequence. It might not stop. Not everywhere at the same time. Imagine a vast cosmic ocean of energy, this quantum field that drives inflation, and it's restless, it's expanding at this astonishing rate. But in some places it's like a bubble forms, a patch of that ocean. It decays, it relaxes, it stops inflating, and it freezes out. That bubble becomes a universe with its own Big Bang, its own space and time, its own matter. That's us. We are inside one of those bubbles. But outside our bubble, in the vast ocean, the inflation doesn't stop. It just keeps going, expanding, stretching, eternally. And as it stretches, it spawns other bubbles, and more, an endless seething foam of creation. Universes, like little bubbles in a foam, constantly forming, extending, floating in this vaster metaspace, entire disconnected regions of space-time, each one, maybe, with its own version of physics. When our bubble froze out of the ocean, the laws of physics, the constants, they froze with it. But maybe in another bubble, they froze differently. Maybe gravity is stronger there. Maybe the speed of light is slower. Maybe there are different particles, different forces. That's eternal inflation. That's one way. You get a multiverse, one bubble in an endless, ever-growing sea, and we can never, ever reach them. The space between the bubbles is inflating, expanding vaster than light could ever cross it. They are completely separate, forever beyond our horizon. We can only infer that they might be there. But then there are other ideas, other ways. There's the many worlds interpretations of quantum mechanics. This one is perhaps even stranger, because this multiverse, it isn't out there. It's not far away in that cosmic foam. It's right here. It comes from the strangeness of the very small. In the quantum world, nothing is certain until you look at it. A particle, like an electron, it doesn't have a definite position. It's just a smear of possibilities, a wave function. It could be here or it could be there. And the standard idea is that when we measure it, when we look, that wave of possibilities collapses. The particle chooses a spot, and that's the one we see. The other possibility is they just vanish. But the many worlds idea asks a radical question. What if they don't vanish? What if at that moment of choice, the universe itself splits? What if every possibility happens? The universe branches. In one universe, the particle is here. In another, a new separate parallel universe, the particle is there. And this isn't just happening with particles in a lab, it's happening constantly. Every quantum event, every interaction, every single moment where there is more than one possible outcome. The universe is branching endlessly. So, in that picture, there are versions of you and me. There's a version of this reality where you decided not to listen to this tonight. A version where you made a different choice this morning. A version where you took that job you turned down years ago. Endless versions, not just of people, but of history. Worlds where that asteroid missed the dinosaurs, worlds where things just went slightly differently. And those worlds, they aren't far away. They're right here, all around us, interwoven, invisible, unreachable, but according to this theory, just as real as the world you're in right now. It's strange though, isn't it, that all of it comes from equations, from math. We don't have direct evidence of these other worlds. We can't see them, we can't visit them. They are by their very nature separate. So why do we take it seriously? Because the theories that predict them, inflation, quantum mechanics, they also predict other things we can test. Inflation, it predicted the exact pattern of those tiny temperature fluctuations in the afterglow of the Big Bang, and when we sent up satellites, we looked, and the pattern was exactly as predicted. Quantum mechanics is the most successful theory in all of human history. It predicts the behavior of particles to an accuracy that is just staggering. Everything in your modern world, computers, lasers, medicine, it works because quantum mechanics is right. And so if the theories work, if all the parts we can test turn out to be true, then what about the parts we can't test? The parts that lead to these strange conclusions, the multiverse. Do we have to take them seriously too, maybe? Maybe we do. There are even other ideas. Some theories like string theory, they require extra dimensions of space. Tiny ones curled up, too small to see, and the way those dimensions are curled determines the laws of physics. But the theory suggests there isn't just one way for them to curl, there's a landscape of possibilities. Perhaps 10 to the power of 500 possible ways, an unimaginable number. Each one a different valley in the landscape, each one a different universe with different laws. Some even suggest that black holes, those strange objects where space and time seem to end, might be gateways. Not wormholes, not like science fiction, but that maybe when something falls in, when information and matter are crushed to that infinite point, maybe it doesn't just vanish. Maybe it rebounds. Maybe it seeds a new universe on the other side, a daughter universe, born from the death of matter in its parent. We don't know, we really don't. These are ideas at the very, very edge of what we can even imagine. But all of these ideas, they point in the same direction. They point away from one and towards many. And that leads to the final looming question. If there are countless other universes, if there is this infinite foam of bubbles, or this endless branching of realities, or this vast landscape of possibilities, then most of those universes must be dead. Sterile, empty universes where the laws of physics just didn't work out. universes where gravity is too strong and they collapse back into nothing a fraction of a second after they were born, or universes where gravity is too weak and atoms never pull together to form anything at all. No galaxies, no stars, no planets, just cold, thin, expanding gas forever. Universes with different chemistry, where carbon doesn't form, where stars can't ignite, where the elements for life are never forged. Just stuck in empty certain realities. And yet, here we are. In this one, this universe where by sheer dumb luck, or by something else, everything is just right. The constants of nature, the strength of gravity, the charge of the electron, the mass of the particles, the rate the universe expands, all of it seems perfectly, exquisitely fine-tuned, balanced on a knife edge. If any of them were just slightly different, a tiny fraction of a percent, the whole thing wouldn't work, stars wouldn't form, chemistry wouldn't happen, life could never emerge. So why this one? Why are we so lucky? This is the anthropic principle. It's a strange kind of answer. It's almost not an answer at all. It says we find ourselves in this universe with these just right laws, not because it's special or likely or designed. We find ourselves here simply because we couldn't possibly exist in any of the others. We are the evidence. The fact that we are here, alive, conscious, and asking the question means we must be in one of the rare universes where observers can exist. In all those countless sterile dead universes, there is no one. No one to look around, no one to measure the constants, no one to wonder, why is gravity so weak? The fact that we are here to observe the universe, it selects the kind of universe we must be in. It's a profound thought, and for some, a deeply unsettling one. It makes our existence, our entire cosmos, seem less like a miracle and more like a statistical certainty. If you have an infinite number of chances, everything, even the most improbable thing, has to happen somewhere. And we are just the improbable result. Still there's something unsettling and wondrous about it. The thought that we might be just one of countless others. That reality, true reality, is so much bigger, so much stranger than we ever had imagined. That this universe, all the hundreds of billions of galaxies stretching for billions of light years, all of history, from that first hot, dense state to this very moment, as you lie here, listening, that all of it isn't everything. It's just one page in an infinite book. One quiet, inhabitable bubble in an endless cosmic ocean. If you go far enough back, if you go back before us, before the sun, before even the planets began to take shape, all you would see is gas. After the universe cooled from that first hot, dense state, it was dark. Not metaphorically, literally dark. No light had ever been emitted, except for that first fading background glow. The universe was filled with enormous, vast cold clouds of hydrogen and helium, the simplest things. Just these vast, featureless clouds drifting, collapsing, pulled inwards by their own patient gravity. Gravity is the sculptor. It works slowly. So slowly. Over millions of years, these clouds began to clump, to condense, little knots of matter growing denser, tighter, hotter, the pressure in the center building and building, until suddenly there's a new kind of fire, a new kind of light. Fusion. The center of that clump becomes so hot, so compressed, that hydrogen atoms had slammed together and become helium, and in that act, a little bit of matter is turned into a lot of energy, into light. The first stars ignite, and that changes everything. The universe, which had been dark for hundreds of millions of years, now has points of light scattered across the black, and with that light comes structure, comes chemistry. These first stars, they weren't like our sun. They were giants, monsters, hundreds of times the mass of our sun, and because they were so massive, they were reckless. They burned fast, they lived hard, and they died young, a few million years. That's all they got. While our sun will live for 10 billion years, these first giants, they were gone in a cosmic blink. But in their living and in their dying, they built the world. Inside the core of these giant stars, that fusion, that fire, it didn't just make helium. When the helium ran low, the star would contract, get hotter, and start fusing helium into carbon, and then carbon into oxygen and nitrogen, layer after layer, like an onion, forging heavier and heavier elements. But there is a dead end, a far dot. When the star starts to build up iron in its core, the process stops. Iron is different. Fusing iron doesn't release energy, it costs energy. It's ash, the fire goes out. And in that instant, that very second, the balance is broken. For millions of years, the outward push of fusion had been holding the star's own immense gravity at bay. And now the push is gone, gravity wins instantly. The entire core of the star collapses in on itself. In a fraction of a second, a piece of the star the size of the Earth is crushed down to the size of a city. The outer layers, which were still falling inward, they hit this impossibly hard, dense new core, and they rebound. A shockwave, a blast of unimaginable power tears the star apart. That is a supernova. A single dying star outshining an entire galaxy of billions of other stars just for a moment. And that moment, that explosion, that chaos, that's where we come from. In that feeble, in those extreme violent temperatures and pressures, all the other elements are born. Everything heavier than iron. The gold in a piece of jewelry, the silver, the uranium, the calcium in your bones, the iodine in your thyroid, the iron in your blood, the very iron that is carrying the oxygen that you are breathing right now. All of it was forged in that moment in a star that died long before the Earth even existed. It's not poetry, it's just the way things are. They are the alchemists of the cosmos. They lived and they died so that the universe could become interesting. These explosions, they blasted these new heavy elements out into space. They enriched those cold dark clouds of hydrogen. The universe was recycling. Nothing is wasted out there. The dust from those explosions mingled with the gas, and the next generation of stars would form from these enriched clouds. Our sun is one of those, a second or third generation star. It was born from the ashes of those ancient giants, and because it had those heavy elements, it didn't just form a star, it formed a system, that leftover dust. The iron, the silicon, the carbon, that debris, that's what formed the planets, that's what formed the rocks, the oceans, and us. But these stars, they didn't just form alone. Gravity was still pulling. They formed in clusters, and those clusters pulled on other clusters, orbiting a common center, pulled by their own collective and gravity into vast spinning structures. Galaxies, cities of light, cities of 100 billion or 200 billion stars, each one a sun, many of them probably with the planets. Over billions of years, these galaxies, they danced, they evolved, they pulled on each other, they merged. Even now, our Milky Way is still growing, it's slowly devouring smaller nearby galaxies, pulling them in, absorbing their stars into its own great spiral arms. And when galaxies do collide, it's a strange, slow, graceful event. The stars, they don't crash into each other, not often. The distances are just too vast. It's like two clouds of dust passing through one another. But the gas clouds, they do collide, and that compression, it triggers new waves of star formation, bursts of activity, lighting up the darkness as a new generation of stars is born from the chaos. And in the center, in the quiet spinning center of almost every one of these vast spiral cities, there is something else, something strange, something unimaginably massive, a black hole, a supermassive black hole, not one born from a single star, but a monster millions, sometimes billions of times the mass of our sun. A quiet, dark anchor that the entire galaxy, all those billions of stars, are orbiting. But that's a mystery for another moment. Still, this is how it begins. Not with us, not with our Earth, but with the stars, born from collapsing clouds of gas shaped by gravity, burning for millions or billions of years and dying spectacularly. And in their deaths, they give us the ingredients for everything. There's something about them, something terrifying and beautiful at the same time. Black holes. Sometimes, when one of those massive stars dies, when it explodes in that supernova, the core that's left behind, it's so massive that its own gravity is just overwhelming. Nothing, not even the matter of the core itself, can resist it. There is no force in the universe strong enough to stop the collapse. The core just keeps falling in on itself forever. And what you're left with, it's not a star, it's not a thing made of matter in any way we can understand. It's a place, a region, in the fabric of space-time where gravity has become absolute, where it has become so strong, so overwhelming that it digs a well so deep that nothing can ever climb out. Not light, not time, not even information. There is a boundary, a line drawn in space. It's not a physical surface, you couldn't touch it, it's just a mathematical line, a threshold. We call it the event horizon, the point of no return. Anything that crosses that line is gone. From our universe anyway, it can never come back. Even light, the fastest thing in the cosmos, once it crosses that horizon, its path is no longer out and its path is only in. And here is where it gets so strange, where our ideas of reality just bend and break. From the outside, from a safe distance, you would never see anything fall in. If you were watching a spaceship or a clock fall towards it, you would see it get closer and closer to that invisible line, and then it would appear to slow down. Time itself, from your point of view, would slow down for that falling object. It would get redder. The light from it, stretched by the intense gravity, shifting down the spectrum, red and redder and dimmer. It would seem to freeze just above the surface, fading, stretching to slowing for an eternity. You would never ever see it cross, it would just fade to nothing. But from the falling object's point of view, from the perspective of the person inside that spaceship, it's different. They would feel nothing. No drama, no bump, no sign. They would just fall right through. They would cross the event horizon in a moment without even knowing it, like crossing a shadow line on the ground. And inside, no one really knows. Our equations, Einstein's equations for gravity, they break down, they give us answers like infinity, which is just the universe's way of telling us we don't understand. Inside that horizon of space and time, they seem to swap roles. The direction inward to the center. It stops being a direction in space. It becomes the future. Just as you, right now, can't help but move forward into tomorrow. An object inside a black hole cannot stop moving toward the center. The future is a place, a single point. We call it the singularity, a point where the density becomes infinite, where all the matter that ever fell in is crushed to nothing, or maybe not a point at tell. Maybe it's just the limit of our understanding, the place where our story just stops. For a long time, we thought that was it. A cosmic dead end, a place where things just vanish. But there's a problem, a huge fundamental problem. It's called the information paradox. In physics, in all of physics, especially in quantum mechanics, information is sacred. It is never ever lost, never. And by information, I don't just mean the words in a book, I mean everything that makes an object what it is, the precise arrangement of its atoms, their spin, their velocity, their connections, the story of that object. Quantum mechanics demands that this information is always preserved. Always. It can be scrambled. It can be hidden. It can be incredibly difficult to read, but it cannot be destroyed. So what happens when you throw a book into a black hole? What happens to the information in that book, the stories, the arrangement of the ink, the the history of the paper. It falls past the event horizon, and it's gone. It heads for the singularity to be crushed out of existence. It seems the information in it is destroyed. And for decades, this was a deep puzzle, a contradiction. And then Stephen Hawking, he showed that black holes aren't perfectly black. They're not forever because of those quantum fluctuations, that restless energy in the vacuum and right at the edge of the event horizon. He showed that black holes leak, they emit a faint glow, a tiny trickle of particles. We call it Hawking radiation. It's incredibly slow, imperceptible. For a black hole the size of our sun, it would take longer than the current age of the universe for it to lose any noticeable amount of mass. But it does happen. Slowly and imperceptibly over unimaginable eons. They shrink, they evaporate, and eventually they disappear. They vanish in a final little pot of radiation. And so then, where did the information go? Where did the story of that book go? If the black hole vanishes completely and the information was inside it, and the faint radiation that leaked out seems to be random, thermal, meaningless, then destroyed. And if that's true, then quantum mechanics, the entire foundation of modern physics, is wrong. But if the information isn't lost, if it somehow gets out, how, where is it? This is the paradox. This is the battleground. It's like a knot in our understanding of the universe, a place where our two most successful, most brilliant theories just stop agreeing with each other. General relativity, Einstein's theory of gravity and curvature space-time, and quantum mechanics, the theory of particles and information, they collide right at the event horizon, and they give us different answers. So we are stuck. Physicists have been struggling with this for decades. There are ideas, strange, beautiful ideas. Some think that the information, it never really falls in. They think that maybe all the information about everything that ever fell into a black hole is encoded, smeared across the surface, the event horizon itself, like a hologram, a two-dimensional flat surface that can somehow store all the info for a three-dimensional image. That's the holographic principle. The idea that maybe the entire three-dimensional inside of the black hole is just a projection of information living on its two-dimensional edge. A whole universe inside, encoded on the boundary. It's a staggering thought. And then there's another idea, a more violent one. It's called the firewall. This idea says maybe Einstein was wrong. Maybe that smooth, gentle fall across the event horizon doesn't happen. Maybe when the falling object hits the horizon, it hits a wall of pure high energy fire, and it's vaporized instantly. That would solve the paradox. The information wouldn't be lost. It would be scrambled and burned and blasted back out as radiation. It wouldn't be destroyed, but it would mean that something is deeply wrong with our understanding of gravity, of space-time. It would violate that beautiful core idea of general relativity that falling just feels like floating. So we're left with a puzzle, a profound mystery, a choice between our best theories. These black holes, they're not just cosmic vacuum cleaners. They're laboratories. They are the places where our current understanding fails. They are a signpost, a clue pointing the way to something deeper, something beyond both of our current great theories, a new idea, a deeper truth, one that finally unites everything. There is this moment, a strange, improbable moment where the dust and the gas, the debris from those ancient exploded stars, it all comes together. It collides, it spins, it clumps, and out of that recycled chaos a planet forms. Not just any planet, this one, this pale blue dot, Earth. And that in itself is remarkable, just another world in an ordinary solar system. But what came after what happened next, that is perhaps the strangest thing of all. Because somehow on this little wet spinning piece of rock the universe learned to think. It learned to observe itself. Let's go back. The early Earth was not peaceful. It wasn't the gentle blue marble we see in pictures. It was violent, molten, battered by impacts from the debris left over in the new solar system. It had no oceans, no atmosphere as we know it. Just fire and rock. And yet even then the conditions were just right for chemistry to begin. As the planet cooled, as the oceans began to form perhaps from icy comets that crashed into it delivering water from the outer solar system, something began in those warm, shallow, primordial seas. Or maybe it began deep at the bottom of the ocean, around hydrothermal vents, where heat from the planet's core bleeds out into the cold darkness. No one really knows, but somehow simple molecules began bumping into each other, linking up, forming more complex molecules, chain structures, and then a molecule formed that could do something extraordinary. It could make a copy of itself. Replication, that transition, that spark, that line between complex, non-living chemistry and the very first flicker of life, it is still one of the greatest mysteries. We don't know exactly how it happened or why here. The solar system had other planets, our neighbours. Venus, for example, could have been a contender. It's almost the same size as Earth. But something went wrong, it's too close to the sun. A runaway greenhouse effect turned it into a scorching hell hot enough to melt lead on its surface. And then there is Mars. Further out colder, Mars did have water. We can see the ancient dry riverbeds. We see the mineral deposits left by what were once vast shallow oceans. It could have had life. Perhaps it did simple microbial life. We are still looking, but Mars is small. Its gravity is weak. It couldn't hold on to its atmosphere and it couldn't hold on to its internal heat. It cooled, it dried out, and it became the cold, frozen red desert we see today. But Earth was not too hot. It was not too cold. It had liquid water. It had a strong magnetic field to protect it from the sun's harsh radiation. It had stability, and it had time, billions of years. Billions of quiet, stable years for that first simple replicating molecule to grow more complex, to adapt, to evolve. And it had help. It had a companion, a guardian. There's something about it that feels almost unnoticed, taken for granted, and yet it is, well, it's almost everything to us, the moon. That distant, quiet silver presence in the night sky. It is more than just a beautiful light. It is a stabilizer. You see, the Earth doesn't just spin straight up and down, it tilts. It leans over about 23.5 degrees, and that tilt, that lean, that is what gives us our seasons, summer and winter, that long, slow rhythm of the year. But here is the thing, the moon helps keep that tilt steady. Our moon is unusually large for a planet of our size. It's almost like we are a double planet system, and that size, that mass, it anchors us. It has enough gravitational pull to keep Earth's orientation stable. Without the moon, the Earth would wobble chaotically. Over millions of years, its axis would shift and tumble unpredictably. Imagine a planet where the axis just flips, where the poles suddenly become the equator, where the climate swings wildly from a global ice age to a fiery furnace. Life as we know it doesn't thrive in that kind of chaos. It needs constancy. It needs that long, slow, predictable rhythm. And then there are the tides, that gentle daily rise and fall of the oceans. It's not just poetic, it's practical. The moon's gravity pulls at Earth's oceans, it stirs them. It mixes nutrients, it drives currents. It is like a planetary breath. And in the shallows, back in those early days where those tides reached furthest, the tidal pools that filled with water and then dried out again and again every day. Some theories suggest that this cycle, this rhythm of wet and dry, this is where life began. That these tidal zones were laboratories, places of chaos, yes, but also of opportunity, giving molecules a chance to bond, to fold, to replicate. The moon may also have helped in another way, by slowing the Earth's spin. Long, long ago, a day on Earth lasted just a few hours. The planet spun like a top, but the moon's gravitational pull created friction, a tidal breaking. Gradually over eons, the days lengthened. The rhythm of life slowed down, and that too may have helped. It gave life time to evolve, to adapt to change. So this silent partner, this sphere of rock hanging in our sky, it is woven into our history, into our biology, into everything we are. And yet for so long we thought this was it. This strange, special, stable system with its big moon and its liquid water. We looked up at all those other stars, and we just saw points of light. It's strange, truly strange to think that for most of human history we didn't know they existed. Planets orbiting other stars, exoplanets. Now we know of thousands confirmed catalogues studied, and probably billions more. It seems that everywhere we look there are stars and around them, worlds. Some small and rocky, some vast and gaseous, some scorched, some frozen, and maybe, just maybe, some like ours. But the first ones, the very first exoplanets we found, they weren't like Earth. Not even close. We expected to find systems like our own small rocky planets close in big gas giants far out. But that is not what we found. The first ones were hot Jupiters. Giant planets bigger than Jupiter orbiting so close to their stars that a year for them lasts only a few days. We didn't expect that. It forced us to rethink everything we thought we knew about how planets form. We detect them in such clever ways. It is so hard to see the planet directly. The star's light is just too bright, it overwhelms the planet's faint glow. So we watch for wobbles. The tiny gravitational pull a planet exerts on its star as it orbits it makes the star wobble just a tiny bit. And we can measure that wobble in its light. Or we look for dips in brightness. We stare at a star, just stare at it for months, for years, and we watch for a tiny dip in its light, a dip that happens regularly. This is when a planet in its orbit crosses in front of the star from our point of view. It blocks just a tiny fraction of the light. It's like trying to watch a single fly pass in front of a giant spotlight from thousands of kilometers away. And from that tiny signal we can learn so much, the size of the planet, its orbit. Sometimes we can even learn the composition of its atmosphere. When the planet passes in front of the star, a little bit of the starlight shines through its atmosphere. And we can analyze that light, see what chemicals are in the air over there. We have detected water vapor, methane, carbon dioxide, and clouds swirling around alien skies. But we keep looking. We keep looking for something else, something more familiar. The habitable zone. That narrow band around a star, that Goldilocks zone. Where it's not too hot and not too cold, it's just right. Just right for water to exist as a liquid on the planet's surface. That is where we hope to find life. Maybe not like us, maybe stranger, simpler, but alive. And we are finding them. Planets in the Goldilocks zone. There is a system called TRAPPIST-1. A tiny cool red star, and it has 7 rocky planets. 7. All of them roughly the size of Earth. And 3 of them are in the habitable zone. They are close not in distance but in potential. And with new telescopes we are getting closer and closer to finding a world that's not just habitable but inhabited. We are looking for biosignatures. Gases in the atmosphere that just shouldn't be there. Gases that on Earth are made by life. Oxygen, methane. Gases that get destroyed quickly, so if you see them it means something is constantly remaking them. And then there's the thought, the quiet, unsettling thought, that we might not be alone, that life isn't unique to Earth, that the universe might be full of voices we haven't heard yet. Or maybe it's silent, vast and empty, and we are the exception. Either way the discovery changes everything, because in finding another world, we are really finding out who we are. There is something about time. It feels obvious, doesn't it? It just flows always and always forward. The past is gone, fixed, a memory. The future is open, not yet here, and we just ride this thin present moment, this now that moves steadily from one to the other. But when you stop, when you really think about it, why does time have a direction? Why can't we move backwards? Why do we remember yesterday but not tomorrow? It's a deeper puzzle than it sounds. Because the laws of physics, the deep fundamental equations that govern the universe, the rules for how particles interact, they don't seem to care. Most of those equations work just as well forwards as they do backwards. They have what's called time symmetry. A film of 2 particles colliding, if you ran it in reverse, it would still look perfectly normal according to the laws of physics. But our world, our reality, is not symmetrical at all. And the answer, or at least the best answer we have, seems to lie in one single idea: entropy. It's a scientific word, but it's a simple concept. It's just a measure of disorder. It's the number of ways a system can be arranged. The more disorder, the higher the entropy. And there is a law, the second law of thermodynamics, that is perhaps the most fundamental law in all of physics. It simply says that entropy always increases. In a closed system like the universe as a whole, disorder always grows. Think of an egg sitting on a table. It's an ordered system. The shell is whole, the yolk is inside, the white is separate. It's in a state of low entropy, and then you drop it. It shatters. The shell breaks into 100 pieces. The yolk and white spread out across the floor. It becomes disordered. Its entropy has increased. And that's easy, that happens. But try to imagine it the other way around. Imagine watching all those shards of shell leap back together. Watching the yolk and white gather themselves up, unscramble and fly back into that perfectly formed shell, which then leaps back onto the table. It doesn't happen. Not because the basic laws of physics forbid it particle by particle, but because the number of ways for an egg to be broken is just astronomically, unimaginably higher than the one single perfect way for it to be whole. So the universe moves from order to disorder, from low entropy to high entropy. That is the arrow of time. That's what gives us a before and an after. We're all just part of this great cosmic unwinding. But that just pushes the mystery back one step, doesn't it? If time flows because the universe is moving from order to disorder, then it means the universe must have started in a state of incredible perfect order. Why was the past so special? Why was the Big Bang, that first moment, a state of such perfect, smooth, uniform, low entropy? That is perhaps the deepest mystery in all of cosmology. The most probable state for a universe is chaos, high entropy, a messy, clumpy, disordered thing. But ours began in this pristine, ordered state, and we have been living off that initial order ever since. The flow of time itself is a consequence of the universe's beginning. And it's not just the state of the beginning, it's the rules that were set. It's one of those things we don't often think about directly. The constants, the fundamental numbers that define everything about our reality. The speed of light, 299,792,458 meters per second. The gravitational constant, the tiny, tiny number that sets the strength of gravity, the mass of the electron, the charge of a proton. These numbers, they just are. They seem to be fixed, immutable, the same everywhere in the cosmos at all times. But why those values? Why not different ones? What chose them? That is the mystery. Because our best theories, our physics, they don't explain these numbers. They are not derived. They are not predicted. They are just inputs. We go out, we do the experiments, we measure the values as precisely as we can, and then we plug them into our equations to make them work, and that feels incomplete. It feels like we're missing a huge part of the story. Because here is the most astonishing thing. If you in a thought experiment, if you change those numbers even just a little bit, a tiny, tiny fraction, the whole universe as we know it, it just vanishes. If you made gravity just a tiny bit stronger, the universe might have collapsed back in on itself a fraction of a second after the Big Bang. No time for anything. If you made it just a tiny bit weaker, the gas clouds would have just drifted apart. Gravity would never have been strong enough to pull them together to form galaxies or stars. No planets, no us. If you change the force that holds the nucleus of an atom together just slightly, then maybe stars could never forge carbon. And without carbon, there is no complex chemistry, no biology, no life. It's like the universe is balanced on a razor's edge, an impossibly thin tightrope, and it walks it perfectly. So why? Why this perfect fine-tuning? Is it just a staggering cosmic coincidence? Did we just win an impossible lottery? Or is it that anthropic principle again? The idea that we, of course, find ourselves in a universe with constants that are perfect for life. Because if they were different, we wouldn't be here to measure them, to wonder about them. It's a neat idea, but it feels a little unsatisfying. It doesn't answer the why. Or maybe it points back to the multiverse. That string theory landscape of possible universes, an almost infinite number of them, each with its own set of rules, its own constants chosen at random. And most of them are sterile, dark, empty, dead. And we just happen to live in one of the very, very rare ones where the numbers came up just right. In the end, we don't know. We just see this exquisite balance, and it drives us to search for something deeper, a reason, a final theory. We've always wanted it. That one equation, the final answer, a single elegant framework that explains everything. We call it the theory of everything. We've come so close in the pieces. On one side, we have general relativity, Einstein's masterpiece. It describes gravity. It describes space and time as a single smooth curved fabric. It describes the large-scale universe, planets, stars, galaxies, black holes. And it works. It works brilliantly. We've tested it again and again. It predicts everything perfectly. But it doesn't do quantum. It doesn't describe the very small. On the other side, we have quantum mechanics, the theory of the very small, the rules of atoms, particles, fields, the strange fuzzy world of uncertainty and probability. And that also works. In fact, it's the most precise, most successful theory in all of human history. The standard model of particle physics explains 3 of the 4 fundamental forces. It explains matter, but it doesn't do gravity. Gravity is the one force it just leaves out. So we have these 2 towering achievements, these 2 perfect theories, and they don't speak to each other. In fact, they seem to contradict each other. When you try to combine them, when you try to ask what happens to gravity on a quantum scale, like inside a black hole at the singularity or at the very moment of the Big Bang, the math just breaks. It falls apart. It gives you answers like infinity and nonsense. And that is a wonderful clue. It's the universe telling us that something is missing, that these 2 great theories are just approximations of something much deeper, a hidden layer beneath both. And that is what the theory of everything is meant to be, a unified theory, a framework that merges the small and the large, the quantum and the cosmic. There are candidates. There's stringtheory, the idea that deep down particles aren't points, they're tiny, tiny vibrating strings of energy, and a different vibration, a different note makes a different particle. An electron is one note, a photon is another. It's beautiful, and gravity just falls out of the math. It appears naturally as just another vibration of these strings, but it also comes with baggage. It demands extra dimensions of space, 10 or 11 of them curled up too small for us to see. And then there's loop quantum gravity, a completely different approach. It doesn't start with strings, it quantizes space itself. It says that the fabric of space-time isn't smooth and continuous, it's granular. It's made of tiny indivisible loops or pixels of geometry. It's also elegant and it solves the problem of the black hole singularity. But the truth is we haven't found it. Not yet. We don't have the final answer. What we have are these profound hints, these deep rules. Hints that these 2 worlds, relativity and quantum mechanics, are not truly separate. That somewhere deep down there is a common language. A single beautiful structure that gives rise to both. And whatever that answer is, it won't just be an equation. It will be a story. The story of why the universe exists, why it has these rules, and why we are even here to ask the question. Across the unfathomable distances of space, through the deepest eras of time, we have watched galaxies ignite and stars be born. We have felt the silent, steady push of dark energy expanding the void. We have considered the end of all things, the cold, the heat, the final quiet dark. And yet, here we are. In all of this vast physical and seemingly indifferent cosmos, something incredible has happened. The universe has woken up. We have spoken of physics, of forces of matter and energy, but now we must speak of something else. We must speak of life, and of thought, and of meaning. This is perhaps the most profound part of our journey. The moment when the cosmos through us opens its eyes. How does this happen? How does inert, lifeless matter organize itself into something that can breathe and move and wonder? There is no magic here. There is no line drawn in the cosmos separating the living from the non-living. Life is not a violation of the laws of physics. Life is the most beautiful and complex consequence of those very laws. Think of the laws of thermodynamics, the rule that everything in the universe tends toward disorder, toward a state of simple uniform chaos. This is called entropy. A broken glass has more entropy than a whole one. A cold uniform soup of particles has more entropy than a star. But life seems to defy this. Life builds order, it creates complexity. A single cell is a universe of intricate machinery. A tree is a masterpiece of chemical engineering. A brain is the most complex structure we know of. How can this be life does not break the rule? It follows the rule in the most clever way. Life creates local islands of order. But it pays a heavy price. To build itself up to maintain its complex structure, a living thing must consume energy. You eat food. A plant absorbs sunlight. And in the process of using that energy, life releases waste heat into the environment. This heat is a form of immense disorder. So the total picture is balanced. Life builds a small, beautiful pocket of order for itself, but to do so it increases the total disorder of the universe around it. Life is a flame, a complex self-sustaining pattern, a river of energy flowing through matter, organizing it for a brief time before that matter returns to the dust. And how does this pattern persist? How does life remember how to build itself? It uses a code, a molecule, deoxyribonucleic acid, DNA. This long twisted ladder is a physical object. It is made of the same atoms as a rock or a star, but it carries information. It is a blueprint, a recipe book written in a chemical alphabet. This blueprint holds the instructions for building a bacterium or a rose or you. This information is passed down generation after generation, a continuous thread of memory stretching back billions of years, back to the first simple cells that learned this trick, the storage of information, the ability to copy that information and to act on it. This is the bridge. This is where physics and biology meet, information written into the very fabric of matter, guiding energy to build complexity, to build life. But even if the laws allow it, we must ask, is it likely we look out at those hundreds of billions of galaxies, each with hundreds of billions of stars? The universe should be teeming with life, it should be loud with signals, with civilizations, but we hear only silence. This is the great paradox. Why is the universe so quiet? It may be that life, especially complex life, is impossibly rare. The journey from simple chemistry to a thinking creature is not a straight road. It is a path through a minefield, a series of near impossible hurdles. These are the bottlenecks, the great filter. Perhaps that the filter is the origin of life itself. Perhaps that first spark, that moment when non-living chemicals first organized into a self-copying system is so fantastically improbable that it has only happened once. Here on this small blue world, or perhaps simple life is common. Perhaps the cosmos is filled with bacteria and algae, but the filter is the leap to complexity, the jump from a single simple cell to a complex one with specialized parts. It took life on Earth almost 2 billion years to make that single step. 2 billion years. Perhaps that step is the barrier. Or perhaps complex life is common, but intelligence is the filter. Look at our own world. Life has flourished for nearly 4 billion years. Dinosaurs ruled the planet for 150 million years, but they never built radios. They never looked at the stars and wondered what they were. Intelligence, the kind of intelligence that can build technology and question its own existence, is not an inevitable goal of evolution. It is a random, fragile experiment, a strange and beautiful accident. And there is one final darker possibility. Perhaps the filter is still ahead of us. Perhaps civilizations, once they become intelligent enough, discover technologies that inevitably lead to their own destruction. Perhaps every civilization that reaches our stage burns itself out in war, or ecological collapse, or by creating something it cannot control. Perhaps the Great Silence is a warning, a reminder of how precious and fragile our small island of order truly is. This fragility brings us to the final, deepest mystery, the one that lives inside your own mind, consciousness. What is it? This is not a simple question. Science is very good at explaining functions. We can scan a brain and see how it reacts to a colour, how it processes sound, how it stores a memory. We can understand the brain as a complex computer, an information processing machine. But why does it feel like anything? Why is there a subjective inner experience? Why do you have a you inside your head? Why is there a feeling of being you? The redness of a sunset, the sound of music, the feeling of sadness or joy or peacefulness. This is what philosophers call the hard problem. Why does all that electrochemical processing in the dark, quiet tissue of this brain generate a rich, private inner world? We do not know. It is the greatest mystery of all. Some believe it is an emergent property. This means that consciousness is not a thing in itself. It is simply what happens when a system like a brain becomes complex enough. A single water molecule is not wet, but when you have trillions of them together, the property of wetness emerges from their interactions. In the same way, a single neuron is not conscious, but put 100 billion of them together, connect them in a quadrillion ways, and the property of awareness simply emerges. It is the wetness of the brain's activity. But others find this unsatisfying. They propose a more radical idea, an idea called panpsychism. This is the theory that consciousness is not something that emerges from complexity. It is a fundamental property of the universe itself. Just like mass or electric charge, perhaps every particle, every electron, every proton, every quantum form field has some tiny basic spark of consciousness, a minimal simple form of feeling. In this view, most matter is conscious in only the simplest way. A rock has a form of consciousness, but it is dull, simple, and unchanging. A thermostat might have a slightly more complex awareness, just enough to know hot from cold. But when matter is organized in a very complex, information-rich way, like in a brain, these tiny sparks of consciousness combine. They resonate. They build up into the rich, complex, self-aware consciousness that you are experiencing right now. In this view, the universe is not a dead, empty place that randomly produces thinking minds. The universe is saturated with mind. And we are not a sudden creation. We are an amplification. We are the universe becoming intensely aware of itself. We do not know which answer is true. Perhaps neither is. But the question itself changes how we see our place in the cosmos. We are here, we are aware, and that is a miracle. Whether by pure random chance or as the highest expression of a universal mind, our existence is fragile. Our time is short. We are a fleeting moment of awareness in an ocean of eternity. And this rarity, this fragility is what gives us moral meaning. If the universe was filled with thinking beings, if awareness was common, perhaps our own would not seem so special. But we are, as far as we know, the only ones. We are the lonely custodians of thought. All the stardust in your body, the iron in your blood, the calcium in your bones, forged in the hearts of long-dead stars, that matter drifted through space for billions of years. It gathered on a cooling planet. It was pulled into the great experiment of life. And now tonight that stardust is arranged into a human brain. And that brain is thinking. It is thinking about the stars it came from. This is the universe. Looking back at itself, understanding itself, through you. You are the eyes of the cosmos. You are the mind of the cosmos. And this gives us a profound responsibility to cherish this small blue planet, to protect this fragile experiment of life, to be kind to one another, we fellow travelers made of star stuff, and to keep wondering, to keep looking up, to appreciate the staggering, beautiful and deeply mysterious reality we find ourselves in. Our journey is complete. We have come from the very beginning, from the silent, timeless point of the Big Bang. We watched the first light break free. We saw the first stars ignite and seed the heavens with new elements. We watched galaxies spin and dance in the grand cosmic ballet. We drifted through the quiet expanses of dark energy. We landed on this world, this island of impossible life, and we looked inward at the very nature of our own thoughts. From emptiness to stars, from stars to life, from life to consciousness. The universe has completed a great loop. It has grown from simple beginnings to a complexity that can contemplate its own origins. And now it is time to rest. All these thoughts, all these vast ideas can settle around you like soft blankets. There is nothing left to do, nowhere left to go. There is only this moment, this peace, this quiet darkness. Thank you for sharing this journey with me. Across all of time and all of space, I wish you the deepest, most peaceful sleep. May your dreams be filled with swirling nebulas and silent shining stars. Good night. Good night.